Wrong pen. Put that over there. Make sure this works. Yep, that works. Damn it. There we go. All right. Good morning. Let me do a quick round of announcements. Let's see here. Move just a couple things on my screen. Okay. Yeah. Let's. There we go. Okay. Today's Wednesday, April 8th. It's the day before the official date of an exam. Of course, things are all a little bit different, but I am keeping that due date of the day before the date of the exam. Please turn in the pre-exam assignment. It's meant to be a quick thing. It's not meant to take a lot of time. Just kind of it allows you to think about what things you want to work on and so on. Make your own list of what kind of problems you expect to see. I found actually that doing this, I think, has increased office hour attendance, at least in the first half of the semester, kind of combined with the other thing that was going on. So I think it's a worthwhile process in general. It's a good thing to think about in front of any exam in STEM. The exam 3 practice materials have been available online. So then tomorrow, Thursday, is technically the date of the exam, but you've got anytime between when the day starts at midnight on Thursday and then at the end of the day on Friday within this 48-hour period, please pick your own 5-hour period of time in which to do the exam. So as soon as you click start the exam, there will be a 5-hour countdown, and by the end of that 5 hours, you should turn in your materials. If you run into some weird error of some kind due to the process, just send me an email. I mean, I might or might not be able to respond right away because I might be doing other things, but just if the first moment you notice something's going wrong for you, just for the sake of timing, just send me an email, and then that creates some documentation for what's going on. Again, I don't want you to take all 5 hours. That's not the point, right? Like, it's just maybe take an hour, maybe an hour and a half, maybe even 2 hours if you really wanted for the exam, and then just wrap things up to take the pictures and upload, and that I hope is only a 10 or 15-minute process. I'm actually thinking of having a fewer number of questions than the practice exam. The downside is each question is worth more points if you're still out of 100. But I think that will help reduce the burden for you a bit. So I think there's a way to do that where it's still fair-ish in the sense that, like, I don't want any one question to be worth too many points either, because that also creates too much high stakesness, and I don't want that. But like, I think there's a way to like ask for different parts within one question without it burning you. Like you can answer one part, and even if that part doesn't work correctly, you can answer the other part, things like that. So I'm working on that. And then the question already came up by email. I expected it to come up, but tomorrow, if you're asking, there is no live class. So at 7:45 or at 8:50 for the next section. You don't need to show up here. I'm not going to say anything. I won't even host office hours. I got to catch up on some grading. So you just do the exam on either Thursday or Friday. I will just wake up early, even though I'm not a morning person. Just sign in, and I'll write it on my screen here to say, hey, in case you missed the announcement on Wednesday, no need to sign in. Either take the exam now if this is a good time, or sleep in, or something like that. Right? Is what I'll post. All right. So I hope that works for announcements. Oh yeah, and then this is a copy of the office hour thing from yesterday. I'm encouraging people to please make use of office hours. Get your questions answered. And the options kind of are all listed here. If audio doesn't work, please call my office phone number. The Murphy Learning Center. I mean, there's options, so please make use of these things. And now let me try to outline what is the story today. So it's a really different kind of class. Today you're not going to see any calculus, but the stuff that we do today will be useful for class next week. So we're starting a new section technically called optimization, and I used to never have a day that looks like what we are about to do today, and it wasn't, let's put it this way, I think this is the 6th time I'm teaching 175, and it was just I hadn't noticed where people were struggling, or I kind of assumed that everybody was fine with something, and it turns out that people were not fine with a certain thing, so I added this class day. So last week we talked about how to find local mins and maxes. The short story you heard summarized yesterday, and I'll super summarize today, was you got to use the first derivative test or the second derivative test. And then Monday and Tuesday of this week we introduced a new thing. We talked about how to find absolute mins and maxes. Yesterday, in fact, I would say we didn't do anything super new. We kind of fit things together, algebra review and logarithms and all this stuff. But yesterday we tried to compare and contrast, like what's the difference between finding local mins and maxes and absolute mins and maxes. And the key point is when you do local mins and maxes, you're going to use f prime to create that sign chart, because you need an f prime sign chart to use this first derivative test. However, for absolute mins and maxes, you actually need the actual y values, right? Like if you were to graph the thing in principle, you're just trying to find the highest up point and the lowest point. So you need to plug things into f in order to get the actual y values, not into f prime. So it seems a little counterintuitive at first, but when you really stop and go, okay, what's going on? What am I doing? F prime, the derivative is the thing that's giving me slope, then it helps fit the whole story together. So that's what we've done. And so I'm saying all this because what we've done so far recently and what we're about to do today sound nothing alike. And if you're thinking these sound nothing alike, it sounds like a totally new story. Am I in the right class today? Don't worry, you didn't walk in the wrong room. Ha ha ha. Both of these procedures, finding local mins and maxes and finding absolute mins and maxes, are used in this thing called optimization, which itself is this kind of grand procedure that puts everything together. The complication I noticed, just in a nutshell, what is optimization? These are word problems, the story problems that sound like this, like find the X that causes the least amount of pollution, or find the X that makes the company the most profit. So I put a least question in there, a most question. There are so many. I mean, actually, just as a brief note, as faculty members, we don't just teach, but we do research. And my research area, if you look on my webpage, is in optimization. And so I, in some sense, work on a fancier version of take derivative set equal to 0. Okay, so here's the thing. Like other story problems, so I mean, just speaking as a researcher in the area, I just bring up 2 applications: least pollution, most profit. And we'll bring up a couple more next week, but I don't want to overdo it, right? Like there are so many applications of this. I mean, if you just stopped me in office hours and asked, I could come up with 100 applications. But I don't want to introduce 100 applications. That would, I think, burden you to like learn a lot of terminology in different areas. That's not the goal here, right? The goal is let's focus on a couple types of optimization problems, so it's not too burdensome for you. And you see, the danger here is like I there's this side of like you know I don't want you to go like, oh, I'm not gonna do this kind of problem, so it's not important as a topic, right? Like if you really want, I can come up with something that's an optimization problem that's in any area, like whether you plan to go in a nonprofit, you're going to work in business, you're going to work for government, and anything at all. There's optimization problems all over the place. So I won't introduce maybe the one that's relevant in your future career area, but it doesn't change the fact that this is super useful. And we'll try to focus on not too many types of problems just to keep things a little organized. And it turns out that one at least very helpful, tangible area to figure out what's going on at first is problems that involve a little bit of geometry. And so the purpose of today's class is to review a bunch of geometry formulas. That's the thing that I had the first maybe 3 times I taught this class. I was just like, oh yeah, everybody knows these geometry formulas, and it turns out I realized that was one of the struggles, so I found a way to fit this into the structure of the class. That said, I think sometimes people run into this thing of, oh, I'm not a geometry person, or I'm not an algebra person, or whatever. The honest view of the two subjects is they're not two separate subjects. I think we sell it like that too often. They're really two connected subjects. And so let's get started. One-dimensional measurements. So quantities that are usually going by names like length or width or height or distance, like how far does it take to drive from La Crosse to Madison, things like that. These are all examples of one-dimensional measurements. So typical units, inches, feet, meters, kilometers, centimeters, miles, and I have the abbreviations there. That's kind of all I want to say about one-dimensional measurements for right now. We will come back to them. The key then is to focus on how do one-dimensional measurements apply to two-dimensional measurements. So a two-dimensional measurement, just generically, is called an area, right? So just in a nutshell, we've got to clarify area from the next thing, of course, which is volume. And so just to put some words to it, like it's asking how much paint do you need, right? Like you're staring at a wall or a ceiling, and you're going to paint it. How much area is there? And then the units are always the previous units, the one-dimensional type unit we were just talking about, with a square. So you can write it notationally like this, inches to the second power. In words, you can call that inches squared, right? Or you can call this square inches. Okay, same deal for the other ones, right? So miles squared or square miles. I think I want to say this. I would say almost maybe not the 3 examples down here, but like this first text. I would say memorize that, not word for word, but I want you to commit to this idea here. So an area formula always involves multiplying, right? So multiplying together 2 one-dimensional measurements. So you might have a length times a width. So the previous slide had those one-dimensional measurements. It might be a length times a width. A one-dimensional measurement might be radius, like of a circle. You might have length times width. You might have length times itself, length times length. You might have radius times itself. But you'll notice in all of the area formulas that there's always a one-dimensional measurement times a one-dimensional measurement, and that might be the same. That second one-dimensional measurement might be the same one-dimensional measurement, or might be a different one. But you'll always find this product, this multiplying together of things. So first of all, this one's the super common one. I think this is the one people certainly know, right? And I will say, yeah, memorize this formula, right? Area of a rectangle, length times width. And that's true whether the length and width are called L and W, or whether the length and the width are called A and B. So if the two sides here are called L and W, of course, you just do L times W. I'm using a capital and lowercase a. I hope that's not too bothersome. Capital A for the area, and then lowercase a and lowercase b for the sides of this second rectangle. But you'll notice here already we're doing this thing of in area, a two-dimensional measurement is multiplying together two one-dimensional measurements, right? Length is a one-dimensional measurement. It's like how long is that string, and then width is a one-dimensional measurement. It's how long is that string. I would say then the area of a square, don't memorize this separately. Why not memorize it separately? Because it's a special case of the rectangle, right? So a square is just a special rectangle where the sides are all the same length. So it's a C here, and then it's a C there. So the area of just applying the rectangle area formula, you have C times C. Of course, C times C, you can simplify and call it C to the second power. We call this, instead of C to the second power, we just often say C squared. Check that out for the name. Isn't that fantastic? C squared, this is a square, right? So C squared is sweet AF. Yeah, I put that in my slides. It's a, right? C squared is a sweet AF way of saying C squared. Because the use of the word square there is because it happens to be the area of a square where the length of the side is C. So even in the naming of C squared, I know we just say C squared all the time when you think in an algebra land, but it's the language was motivated way back when by geometry. Okay. Area of a triangle, you may have seen the formula, but I just want to convince you that it works. So take a look at this big, there's a big rectangle, and then if you just join two opposite corners of the rectangle, then you get this red triangle, and I want to talk about the area of that red triangle. You may have already heard or memorized that the area is a half times base times height. But I think it's super convincing when you look at the picture, right? Because that same red rectangle, you see the same amount of area in white, just an upside down flipped version of that triangle. So the red triangle should be half of the entire rectangle. So that's why it's a half times the length times width from earlier. It turns out that you again have 1/2 times A times B for this yellow triangle. It's in fact a copy of the triangle above. I just changed the names of the height and width from L and W to A and B. But even if you were to slide this point over, so all I did in the computer was I dragged this point a little bit this way, and then I screenshotted that and put that over here. So the height and the width should be still perpendicular to each other, so that's why the height isn't this way, but it is that I have this I-beam here to indicate that this is perpendicular to the base down here. So the area then is, for both of these yellow rectangles, is 1/2 times the base times the height, so or 1/2 times A times B. Of course, if you prefer, you could write that as A times B over a 2. It's just the 2 is in the denominator either way you do it. And the argument I usually give is like I in class I would stack a bunch of books this way, so that all of the ends of the books are kind of together, and then start pushing books over, and you'd create this shape. This obviously, this demo, I don't have actually that many books at home. All my books are in the office, which I'm not allowed in. So I can't do this demo. So I was looking online to see if I could find a good explanation of it. And I found an explanation that's even better than the books thing. So if you'd like, this is an optional video to watch. It's 4 minutes. It's not my video, but I actually like her explanation much better than mine. So I'm actually going to adopt that next time I teach this class. But if you're cool with it, you're like, I don't need to watch it, I'm convinced that the area of both of the yellow rectangles is either of these two formulas. Cool. What about perimeter? So perimeter is about how long it takes to go around the outside of an object. So in this case, there's an L here. And if you start walking, like starting in the upper left corner and you walk down, you've walked L, and then you've got to walk to the right, and that's a W. But then from here, you're not done. You've got to walk up, so plus L. And then you've got to walk to the left, and you'll have plus W. So this is honestly the way I want you to think about perimeter. Is you might have learned a different formula. You might have memorized something, or you might think you've got it memorized, but memorize something incorrectly. I want as much as possible to memorize few things and then to build from there. And in the case of perimeter, I think it's much nicer to just go, oh yeah, it's L plus W plus L plus W. Of course, you can collect like terms, right? So the L plus L, those two L's I circled, you can combine and have a 2L. Same with the W's, you can combine them and get a 2W. So often people are just presented 2L plus 2W, but sometimes people memorize it incorrectly, I guess, and people have like L squared plus W squared, things like that. Um, I think it's more important to see where this comes from. And you're going to see this theme throughout today. Like, even if some of these formulas you're like, I see where they come from, I think by the end of class today, you're going to see some formulas where you're like, oh, yeah, okay. So try to avoid memorizing. There's a couple places already in slides you saw I put in caps. Memorize. Yeah, there's times that's appropriate. There are times when it's going to get you in trouble. So I want you to, if you're ever stuck, you can come back to the recording of this and go, oh yeah, that's how this was done. I want you to reason through this. Okay. Perimeter, just to frame this right, let's make sure to clarify. This is a one-dimensional measure, right? So this is a one-dimensional measure. Is like how much string is used to go along here. It's not how much paint. So the units on perimeter would be in inches, meters, miles, that kind of thing. So you always want to be careful. I say this because in word problems I put in the reminder. On quizzes and exams, please include appropriate units. And I've seen things like asking for perimeter, and people will report their final answer in square inches or something because some other part of the problem dealt with area or something like that. So please be careful about that kind of thing. Okay, circles. The circumference of a circle, that's the distance going all the way around, how much string is needed to go all the way around. It can be called perimeter in some circles. Oh, I did not even mean that. That's so bad. All right, in some places people do call this thing perimeter. It is the formula to memorize is 2 pi r, so that one is a memorized one. The area, how much paint is needed to paint the interior of the circle, that also has to be memorized, and that is pi r squared. So these are two formulas that do need to be memorized. I want you to try to not swap them for each other. Sometimes people put this one there and that one here. Don't do that. So here's where the comment made earlier today, I hope, is helpful in going, okay, here's what's actually, so the thing is, notice the area. You've got pi times r times r. So you have this thing going on of what we said, of multiplying together a one-dimensional measure and a one-dimensional measure, a radius times itself. An area formula, as I maintain, always has a one-dimensional measure times a one-dimensional measure. So that's consistent. Like, that will never change. Okay, so that's one way to think about it. I hope that helps. Let me give you another way to think about it if you'd like. So what I'm about to say is an optional thought, meaning please listen into the explanation, and I hope I can convince you of what's going on here. And if you're like, oh, I did not like that way of thinking about it, then ignore it. But I just want to give you, here's one way to try to keep the two formulas sorted, but here's another way. So let's think about the area of this circle, and then what would happen if you increase the area just by a little bit. Now, I wish, first of all, I can't trace that great on screen, but I wanted to draw a circle whose radius is a little bigger. And I mean, if I had like a whiteboard, I could use another color and just basically draw so that the red circle and the blue circle are touching right on their border. But the point is, how much more area is in the new circle? Well, that's the change in the area. So if you have the area formula memorized properly of pi r squared, then we can ask about the change in the area, right? So thinking of r, the radius grew just by a little bit. So as r changes by little, so r is like the x variable. What happens when you take a derivative? You get pi is a number, so it should just be copied, right? Plain number copied by the constant multiple property, and you differentiate r squared, and you get times 2r. Of course, these are just three things multiplied together, the pi, the 2, and the r, so you can switch them in any order, and you get 2 pi r. And actually, it makes sense that the change in the area is just 2 pi r. That was the circumference. That's just like how much string is in this space right around here. Right? So if you grow a circle by just a little bit, what was the change in the area? It's just that pizza crust. I mean, if there's like a very tiny outside pizza crust. So it's kind of neat to see that the derivative of the area is the circumference, because that's how much the area changes by. It's by just how much of the circle you go around once. So that's sort of one sort of spot check way to do things. If like you think you've got the area and the circumference memorized in the right order, think about it geometrically like this. Take what you called the area, differentiate it, see if you get what you should expect or what you thought was a circumference, and if you don't, maybe you need to swap the two, and then you can do that check again of differentiate the area formula that you had, see if what you get was what you called the circumference. If so, then life is probably groovy there. Okay, so I'll just pause for a moment. Again, if you don't like that explanation about how the derivative connects together, the change in the area is the circumference, then don't worry about it, but it's kind of a neat way to view and review what the heck the derivative means. I mean, the derivative is a slope, and the slope is quantifying change. So, okay. All right, so then I'd like to move to three-dimensional measures, and we will, by the end of class, please don't tune out. I mean, I will say things that I think are familiar, but I'm going to bring up a couple other things by the end. A couple two-dimensional measures come back, and then something else shows up as well. But a three-dimensional measure is like you've got a solid object, maybe a cup, and you're asking like how much air would be contained inside, or how much Play-Doh can you stuff inside of it. The units are now things like inches cubed. So this, I think it's good to keep in mind as just a spot check all the time. Just like the comment for an area, where an area had to be a one-dimensional measure times a one-dimensional measure, a volume always multiplies. Product is just a fancy word for multiplies. A volume formula always multiplies together a one-dimensional measure and a one-dimensional measure and a third one-dimensional measure. It always happens. You always will see, a length times a length times a length, or a length times a height times a width, or something like that. So here's the area formulas we've looked at, rectangle, triangle, and circle, and I want you to think of volumes as repeated area. So what if you had this rectangle here, and it wasn't like, flat on the wall, but like you turned it on its side so that it ended up being the floor of a building, and then you have many copies of this rectangle. It is repeated. So here's my attempt to draw that. So this one rectangle is up here, and then below this you just have more and more copies of this rectangle. I shouldn't draw too many of them because it'll get too messy. So then the volume should just be this area from before, L times W, and then multiply by how many copies of this you have. So if you have like 5 centimeters worth of this, then you would multiply by 5. Same general deal. So if the area of a rectangle is 1/2 times the base times height, or 1/2 times length times width, then if you had that triangle shape, and then you had just copies of this underneath three-dimensionally, then you take that 1/2 times length times width and then multiply by that h. Same deal, one more time here. Circle, you'll see the circle area right there in the volume formula. You just have a multiply by h again. So all of these, I don't want you to memorize these volume formulas separately. Is the comment down at the bottom? Sorry if it's not showing because of maybe you might have to download the slides to see some of the comments down there if the WebEx buttons are in the way, but I'll read it aloud. It says, don't memorize these volume formulas. See how these are connected to the area. Right, each time you take one of the corresponding area formulas above, and you are just multiplying by that repeated h. That's what's happening here. Okay, so let's practice some things and say, like, let's say you have a rectangular box and it has a square base. What is an expression for the volume? You're going to see a lot of this kind of language of square base. So I know it happens every semester in this class. Like about 2 weeks from now in web work, people are like, I'm missing something, and I say square base, and they go, oh yeah, that. All right. So first of all, the the general formula we just saw for the volume of a box is going to be multiply the three one-dimensional measures. So maybe they're called L, W, and H, or we'll just assume that. You get to pick the letters, I guess, because it wasn't provided in the question. But if you draw that picture, so generally speaking, here's, by the way, how to draw a box. That was another thing actually that I learned actually only literally the last time I taught this class, is that sometimes people struggle to draw what a box looks like. So let's talk about it actually. So I tend to just draw a parallelogram, and what I try to do is this point that's here, I try to make sure that it's not drawn directly underneath this point. What I mean is sometimes people will draw like this, and then so this point is directly underneath this point. You want to avoid drawing like that if possible. Try not to do that. The reason why not is what you do is once you've drawn, that one's messy. I'm gonna just redraw. I'm gonna erase and redraw since I explained what I meant by that. So after you draw, this is meant to be a rectangle. I know it looks like a parallelogram, sort of tilted, but it's because of the 3D perspective. What you do is you draw an exact replica, a copy of this directly underneath it. Just literally, just shift, your hand down on the paper and draw the same shape. Then what you can do is you can connect the corresponding corners. So the lower left connected to the lower left, the upper right connected to the upper right, and so on and so forth. I think that's the easiest way to draw a box. Now, in your usual box, you have a length and a width, and then usually, the height is usually drawn sort of the z that direction. Now, this is perfectly fine right here, technically for the volume L times W times H, but I want to practice this thing about square base, and square base means that down here, this bottom rectangle that I'm shading in. If that's a square, that means this tells us additional information about L and W. We don't know what number L is or what number W is. That was not given to us in the problem, but we do know that they're the same number. So what we're trying to say here with square base is that L is equal to W. Right? So I'm not going to redraw the picture. I would have to shorten up this line segment a little bit to make it look more like the same length as W. But the point is, square base, so L equals W, and the point is if you replace, that means if L really is equal to W, that's the guarantee from the square base part, then you can replace this L right there with a W. So then you'd have W times H, which I just simplified the W times W as a W squared. Or if you prefer, you could, instead of replacing the L, you could replace the W. You could replace the W with an L, and then you'd have L times H, which I've written as L squared times H. Your call. To me, both of these are perfectly valid final answers to this question, and they're as simplified as possible. You might say, this seems strange, but next week we're going to see word problems that have sometimes 3 variables, sometimes 5 variables, sometimes 6 variables, and anything that we can do to get rid of a variable in a valid way, not just erasing a variable, but anything we can do to substitute to get rid of a variable is a really good thing to do. So this is meant to be a warm-up to the kind of thing we're doing next week, right? So this is totally a valid volume formula, but to prepare for next week, one of these two versions is preferred because it has one fewer variable appearing in it. Next question, let's try this. Suppose a rectangular prism, so that just means the same thing as rectangular box, of dimensions 2, 3, and 5, has the same volume as a circular cylinder. So write an expression for the height of the can in terms of the radius. This is also a very common type of task. It appears as one part of a bigger problem next week. There's actually 2 different 3-dimensional objects. There's the box and then there's the cylinder. We need the volumes of both because, well, they have the same volume, but we need both volume formulas. So first of all, let's deal with the part where we have the numbers, right? So the volume of the box, multiply the 3 one-dimensional measures, you get the number 30. So this, we know the number for the volume of the box, and then the cylinder is supposed to have the same volume, so I'm just going to plug in. Like in the formula for the cylinder, V equals pi r squared h, so pi r squared was the circle area formula. I'm just plugging in for the v part because we were told same volume. So with the volume of the box of 30 is plugged into that spot right there, and you have 30 is equal to pi r squared h. We're not done. The question says we need to write the height in terms of the radius, meaning the height of the can, which is using the variable h, we need to write that. So that means the language is maybe slightly fancy, but we need to solve for h. So it's not so bad here. All we got to do to solve for h, all these things are being multiplied. Sometimes people make these strange algebra errors of wanting to subtract on both sides, but there's all this stuff is multiplied over here. Pi times r times h. So the undo multiplication, you got to divide. Don't subtract. Yeah, so lots of algebra things, I guess, come up. So sorry if I'm mentioning things where you're like, come on, I knew that. But like, we got to undo multiplication, we got to divide. So divide both sides by pi r squared, and you have 30 over pi r squared is equal to h. That's totally fine as a final answer to question 235. However, I would like to suggest we write our final answer in another format that's also valid and is more useful next week. So I'm going to swap the two sides. Not that that really changes anything. So the h is written on the left side. But what I did is you'll notice the 30 is still in the numerator. Pi is still in the denominator. But I wrote the r thingy no longer in the denominator. But if it was an r to the positive second in the denominator, then once it moves to the numerator, it has to be an r to the negative second. Right? So whenever you swap where something's written in your fraction from top to bottom or vice versa, you got to take the exponent and make it the negative of what it was before. Why are we doing that? The comment here is this is nicer if you need to take a derivative. Yeah. Spoiler alert for next week, we will differentiate this. Or things like that. So both what I just circled and the previous thing here, both lines have a happy face, both are technically correct, but I would not like to differentiate this version of h because it would require the quotient rule. I would like to differentiate this version of h because all I got to do is the constant multiple rule followed with the power rule. That's much nicer. Okay, maybe I'll pause here, see if we're all doing all right. Give a couple seconds. All right, so let's talk about surface area. It is an area, actually. So you might say, wait, we're starting with a three-dimensional thing, and we're talking about a two-dimensional thing that comes out of it. So you have this three-dimensional thing, and now you ask, how much paint do you need to paint the outer shell of this thing, of this object, right? So let's start with one of the easiest cases is this rectangular prism. I want you to see that there's 6 sides of a rectangular prism, just like when you play a board game and you roll a dice, there's 6 sides on that. It's just the 6 sides of that little cube dice are all maybe all the same looking shape. They're all squares. In a box, it's just elongated differently. But the 6 sides, I want you to notice that the top and the bottom are actually the same shape. Like they are of the same area. So I can shade and then delete here. So like that top rectangle and then this bottom rectangle here, they're just like the bottom one, if you just raise that up, the top one is just hovering above the bottom rectangle and they're the same area. And both of those areas, let's see which of these 3 letters apply between L, W, and H. It looks like it's L, that one, and then W. But you've got 2 of them, right? So you have LW plus LW. That accounts for the area at the top and the bottom. But let's think about where else there's okay, that's 2 of the 6 rectangles. Where else? Well, there's the front and the back. What I mean by front and the back is like the front one, I'm not going to shade it in because they're going to run into each other, but I can outline them. So that's what I mean by the front rectangle. And then there's a back rectangle over here. And both of those are rectangles which apply. Well, it's the H and the W from the rectangular prism, from the three-dimensional object. So we have a WH plus a WH for those. And then where else? There's 2 more rectangles. They're the most hidden ones. Do you see them? I would like to call them the left and the right rectangle. I think that works for language. So let me I could actually shade those ones in. They're not going to run into each other. So that one and this one, right? And if you see which letters apply there, it's the L for this. Now it's too messy. Okay, so for this rectangle, the L side and then the H side. So L times H, but two of those, right? Because the left one so one's for the left and then one's for the right. So piecing this all together, the total surface area is add all of these together, right? So LW plus LW plus W, So, and notice this is a surface area. So, as all area formulas have, we have multiplying a one-dimensional measure and a one-dimensional measure. So, like a length times a length times a width, for instance, or a width times a height. And of course, you can collect like terms. So, the LW plus LW, you can have a 2LW. The WH plus WH, you can have a 2WH. But I think it is not. I stress that it is important not to memorize it like this. I mean, you got to know where these twos come from. I know this sounds ridiculous, maybe. You might say, oh, I'll be fine without this. I've had students run into trouble every semester just ignoring this advice. Like, it's not worth it. If you understood the explanation given here, then you should think about it this way. Please think about it this way. Especially for what we're about to say in about 10 minutes. You got to think about it this way. If the explanation's unclear, you should unmute a mic and ask a question. You should put a question in the chat or say, please re-explain that, or something like that, right? Like this is super critical to say that we just took this box and like identified parts of it and said we can find those individual areas and then add them together. Memorizing is going to get you in trouble here. Okay, if we're cool with that, then here's the next one. Okay, another surface area. Surface area of a can. The can, I would say, has three sides. So there's the top, there's the bottom, and then there's the part around. So the top is a circle, right? So the top right there, that's a perfect circle. Sorry, it looks like kind of an oval because I tried to slant the picture a little bit because of the 3D perspective. But that circle, if we recall just a moment ago, the area of that circle is pi r squared. And then what about the bottom? Well, that's the same circle, right? I mean, it's a copy of that same circle physically in a different location. It's just lower, but it's exactly the same size and shape. So that circle should also have an area of pi r squared. What about the part around? You get what I mean by the part around? Now, I don't know if you have my camera view, but I have this can, and I thought if I just do this in the little window, you're not going to see it really well. So I tried to do something else. What I did was I created a little YouTube video on Monday, and I'm going to play it. The issue being, I know that you're not going to hear any audio. So I knew that, but I narrated audio anyway for if you click on the link later. And so I'm going to play not the entire video. It's 4.5 minutes. I'm going to play part of it, and then, but I'm gonna still talk right now. So you're not going to hear. So there's the area around, right? Like I'm holding onto this can. There's the top. We're not talking about that. There, I'm pointing to the bottom of the can. We're not talking about that. The area around the can is where the label is. So if we want the area of that, the fortunate thing is we can take a pair of scissors and try to be careful with. So, okay, right? So I chopped down the side and hoped that this will rip decently, and it actually ripped rather cleanly. I should actually just try to play this at double speed here. So yeah, let me change speed this up. I can still narrate. Okay, so wow, now I'm working twice the size. Okay, the towards the end though, the on one place the sticker was sticky, so things ripped funny. But take a look at the shape that we have, right? After ripping off this, the shape is literally a rectangle. I mean, other than cutting poorly, and so what's the height of this rectangle? Right, that right there, the height of the rectangle. Where do you see it on the can? It's the height of the can. The height of the rectangle is the height of the can. I don't know what oh, the sticker was sticking to my finger. Okay. And then what about that side? The other side of this rectangle. Where do you find that on the can? Right? That's the circumference of the can, isn't it? It's going around. In fact, I'm going to show by taking the label, which keeps sticking to one of my fingers, and I turned the label upside down where there was less glue, and you'll notice that that the other side of the rectangle is going once around the can. Okay, I'll stop the video. And the point here being, so normally this is a demo I actually literally do with cans in class, but I thought this was the most effective way to do this here, was pre-create a video. The whole point is if you unravel, and you just kind of lay this out, you have a rectangle, and the height of the rectangle, or one side of the rectangle, is the h that comes from the can, and the other side of the rectangle is 2 pi r, the circumference formula for a circle. So when you multiply those two things together, I just stuck them in parentheses here, but it's all multiplications, so there's no distributing business or anything like that. You just drop the parentheses and then write the things in any order you want. So I wrote 2 pi r h, 2 times pi times r times h. Okay, I hope that's really convincing that the area around the side, the third and final side of the can, the round side, the area is 2 pi r h. So then all we do for the total surface area of the can is add these three things together. Add together pi r squared, the other pi r squared over here, and then add this final thing in its simplified form, 2 pi r h. Of course, so in these three terms that you see here, the first two terms are of the same type, so you can collect like terms. So we do that. And when you collect like terms with pi r squared plus pi r squared, you have here 2 pi r squared. There's still, separately, let me circle it, there's still the 2 pi r h. So all that happened from the line here that says total surface area of can to the simplified version is collecting together the first two terms. Now, I need to say, please don't memorize this. If you memorize this, what I'm about to say on the next two slides is not going to make any sense at all. In fact, the important thing here to note is this 2 and this 2 they come from very different situations, right? So the first 2 comes about because you are collecting like terms. There was a pi r squared for the top of the circle, the circle on top of the can. There's a pi r squared for the circle that was the bottom of the can. And then over here, what about this other 2? Oh, whoops, I clicked on a link here. Okay, that link. Okay, the other 2, I need to probably stop a video here for a second, excuse me. Okay, there we go. The other 2 it did not come from collecting like terms at all. This 2, track where it came from, back here, was this 2. It was just the 2 that literally just happens to appear in the formula for the circumference of a circle. So the 2's come from very, very different sources, very different places. That is super important to know. I want you to understand this formula, not memorize it. Okay, I'll pause because this is maybe the strangest of the formulas and see how we're doing so far. Okay, if we're okay with this, then what we now talk about is there's sort of the next thing we look at is based off of surface area, but it is not surface area itself. Like so, you take portions of your geometric object, and perhaps there's different costs assigned to different parts. So we take pieces of the surface area and we manipulate them and do something with them. Yeah, so the reason not to just memorize the surface area formulas is cost. In order to come up with cost is, by the way, a very, very important thing in any kind of business where a final product, a physical product is produced, right? Like you're going to make something, you sell something to the public, unless the thing you are selling is all made out of one material, it's like literally all the same metal, you're going to have to deal with costs that have different materials in them. Like maybe there's a plastic side, there's a metal side, there's a little, piece that's made out of PVC pipe or whatever. Like you've got to deal with costs that of different materials, even in just one product that is sold. So as a warm-up, let's look at this. The cost of cardboard is $3 per square inch. Write an expression for the cost of making a rectangular box out of cardboard. So we already said that the area, or the surface area, of a rectangular prism or rectangular box is this. And once you collect like terms, 2LW plus 2LH plus 2WH. And how does this area, I mean, we don't have the numbers L, W, and H specifically, but that box thing is a way of representing the area. How does that relate to the 3? What do we do with these two things? Well, what I want to do is create a separate question off to the side that helps make it a little more concrete what's going on. Because staring at this formula sometimes I think makes things a little too abstract and people like not get a little confused. So if you're like, what do I do with this, and how do I take this underlying thing, and what do I do with the 3? Then off to the side, just make this situation. I'm just making things up. This is not part of the question. This is just this separate thought allows us to think about the question appropriately. So I'm going to just make up a number. I just made it up. Let's just pretend that the area was 100 square meters. So even it might not be, but let's just pretend for a second that what I just circled is 100 square meters. So if you've got 100 square meters of area, like that's how the outside of the box, or that's where all the cardboard is. Oh, whoops, I see a switch of units. I didn't mean to do that. So let's change this to inches so that it matches the per square inch. But if it's 100 square inches and $3 per square inch, you got to pay that $3 for each square inch. So you got to multiply these, right? $300. So the key point is to find out how much money needs to be paid, you do 3 times 100. Well, if that's what you do there, knowing that the number here is a 100, you ought to do the same thing here. It's 3 times this formula version of the area. And so that's what we'll do. So we learned, the point is from this process that we need to multiply the cost per area unit by area in order to get the actual cost in dollars. So that's what we do here, right? So the cost, we actually had seen cost was labeled with a capital C in the past, so we'll do that here. You should take the area that we had before, because there's several terms I thought it's actually safe to put that in parentheses. In fact, we need to put that in parentheses, and take that and multiply by 3. So I hope, other than my mixing up of units here, it should all be the same square inches all the way through. Hope that works. As a follow-up question, I would like to now I copy pasted this equation, just this part there, down here in the next question, and I would like to solve for L. Okay, this is a very common type of activity, taking an equation that looks like the equation you see in 237 and solving for L. That's a very, very, very common type of activity for next week. So you could distribute the 3 or not, your call. I think most people are going to. I actually probably wouldn't, but since it's the thing that I think most people are going to do, and it'll work, I'm going to do that. So distribute the 3. Now we don't have, like over here at the end, it was like a 3 times another big thing. So the right side used to be multiplications as the final activity. Now the final activity on the right side are additions, meaning that you've got terms on the right side. So to undo terms, you would need to add or subtract. All right. So earlier, you recall, we had as our final operation was multiplication, so we had to divide on both sides. Now to do anything meaningful, you've got to subtract or add on both sides. Notice where the L's are. If you're going to solve for L, there's one right there, there's one right there, but there isn't one in the third term. So let's get all the terms that have L on one side and the terms that don't have L on the other side. So I'm going to subtract 6WH from both sides. And you'll have capital C minus 6WH equals 6LW plus 6LH. Now what? Well, literally all the terms that have L are on one side and all the terms that do not have L are on the other side. This is good. Once you have all the terms that have the variable you are solving for on one side, then literally, because all terms over here have the variable, I mean any terms that didn't, by design you subtracted them to the other side. So what you can now do is factor out that variable L. So factor L We didn't do something to both sides. I just factored out L. Remember, factoring always produces a new set of parentheses here. And the great thing about this is it works. The factoring works because every term had an L. Any term that didn't, that was going to cause a problem. We subtracted on both sides anyway, so it didn't appear. And then the great thing that happens is in this previous line, there were two L's written, right? There was an L in one term, there was an L in another term. And that's a problem to try to solve for L. Now look, there's only one written L. We only write L one time right there, and that's awesome. Now, to solve for L, look, it's L times this other thing. The final operation is multiplication, so don't try to subtract. You got to undo the multiplication by dividing on both sides. So the original C minus 6WH that was on the left side before, now divided by 6W plus 6H. By the way, none of the 6's here are going to cancel. You don't have any of the 6's being factors. Okay, let's do just a handful more here. Let's see how timing, yeah, let's do this one. Yeah, okay. The cost of cardboard is $3 per square inch and plastic costs $4 per square inch. I'd like to write an expression for the cost of a box with 5 cardboard sides and a plastic lid. What I mean by plastic lid is this top part right there. That one rectangle at the top that's shaded is made out of plastic. So the area of the lid, that shaded, the area of the lid is LW, right? Just this one rectangle on top, and that area, you should multiply by 3, or sorry, by 4, yeah, because the lid is made out of plastic, yeah. So if the plastic costs $4 per square inch, you take the area of of LW with 4, you multiply by 4. The area of the other 5 sides, this is exactly why you don't want to memorize the surface area formula, is the other LW, that's the rectangle on bottom, plus the 4 sides around. So then if that's the surface area for the remaining 5 sides, and these 5 sides are to be made out of cardboard, 5 cardboard sides, then you would have to multiply by 3. So 3 times that quantity. So you've got one cost over here. That's how much money has to be shelled out to make the lid. Here's how much money has to be shelled out to make the other 5 sides. So the total cost is you got to add them together. And we won't simplify that any further in this. I've got one last one for you. The metal for the base of a can costs $7 per square centimeter. And the sides, that's the round, around like where the label is, costs $11 per square centimeter. So what is the cost of a can that doesn't have a top? Like it's intentionally missing the top. So there's no circle up here. It's just open, empty space. Well, then the area of the base down here, the circle that counts, pi r squared, and then it costs $7 per unit of area, so you would take this area here and multiply these two things together and have 7 times pi r squared. You could drop the parentheses if you want. Then the area around the side, recall earlier, was multiplying the, I wrote it in this fashion to remind you that we're talking actually about a rectangle that just is different in shape. It's a curled rectangle. But if you uncurl it, you have this. And then the side costs $11 per unit of area. So if you have this much area, you would multiply these two things together and have 11 times 2 pi r times h. So then the total cost, there's no top, right? This can is missing a top. So then the total cost of building a thing like this would be that thingy plus that thingy. I just wrote it a little differently by not writing my parentheses here. So I think I will just comment that you need to understand instead of memorizing most of these formulas. If you just try to memorize the surface area formula, you're going to get totally stuck with the cost thing. Cost and area and volume are all different quantities. They have different units. So please never set a cost equal to an area. Don't set an area equal to a volume. They're different kinds of quantities. And the real comment here to say is that these ideas are warm-ups to the things that we will look at next week. Okay, same announcements, right? No live class tomorrow in case you just joined late today. It happens because people still sleep in. So if you sign in at 7:45 a.m., I will set this up on screen that there is no class, but I will be grading things from my other class. All right, see you in office hours, perhaps. Otherwise, please do the exam.